Hi guys, welcome back to my YouTube channel. I'm Len with B, and today we will be talking on thermodynamics. Yes, so before we get into the topic, if you're a first time on this channel, please kindly hit the subscribe button, and if you've subscribed, thank you. You're welcome back to this channel. So let's get right into the topic.
So, what is thermodynamics? Thermodynamics is the study of the transformation of energy and the accompanying changes in the state of the involved matter. It provides understanding on how energy is transformed and conserved in various processes. It is also the study of the relationship between heat, work, temperature, and energy. So let's assume our involved matter is the system. Don't worry, you get to know why our involved matter is the system later on. But let's just put system in place of involved matter. So that leads us to thermodynamics is the study of the transformation of energy and the accompanying changes of the system. So now our system is like the area of focus. The involved matter is like the area of focus, the aspects at which we are interested in. So now, thermodynamics is just to let us know and help us understand what happens within that thing that we are focusing on, our area of focus. What happens within the area of focus, the kind of transformation of energy that happens there, the accompanying changes that happens in the system. That's the area of focus. That is what thermodynamics is all about. It's to help us know and to help us understand how those energy is being transformed, how they are conserved in various processes, probably from how they move from one energy, or how they change from one energy to another, or how the energy is just being transformed basically. So it's the third point says it is also the study of the relationship between heat, work, temperature, and energy. So thermodynamics also help us to know the connecting dots between it and work, like what connects it and work together in a system, what connects it and temperature together in a system, what connects it and energy together in a system. So thermodynamics help us to know the connecting dots, help us to understand the relationship between it and work in a system, the relationship between it and temperature in a system. So in sum, you can just say thermodynamics is just to help us know what happens within a system. That's basically what we can say thermodynamics is all about. Like I said, in summary, it's just to help us know what happens in the system, and whatever it is that happens in the system, like probably the heat that is added or removed in the system, the work that is added or removed in the system, the energy that is added or removed in the system, the kind of temperature that happens within the system. So that's basically what thermodynamics is all about. So the next thing we'll move into the relationship between thermodynamics and food science. So you might be wondering what's food science business with thermodynamics? Like why are we related? So now relationship between thermodynamics and food science answers the questions: why do we need thermodynamics and food science? Thermodynamics plays a crucial role in food science and technology, impacting various aspects of food processing. So food science and technology has a lot of like branches. We have the food processing, we have food preservation, we have food quality, we have food engineering, and thermodynamics plays roles in these processes. In during our food processing, for example, I mentioned that thermodynamics is about what happens within the system. So now, when we are processing food, for example, the equipment that we use in processing our food, what happens when we put our raw material into the process, and when the raw material process whatever it is that we want to process and gives us our final result. So what happened within that system is why food science and thermodynamics is related. So yes, so food preservation to what we use basically most times. This thing is just the reason why thermodynamics is really the reason why we are really concerned with thermodynamics is because of the things that we use to do most of our food stuff, even if it is processing, if it is preservation, the things that we use in preserving them, the equipment that we use in preserving them, what happens within that system, how heat and energy is transferred within that system. That is why food science is related to thermodynamics. It optimizes its transfer in food processing equipment. And I already said it's basically our equipment. So thermodynamics governs its transfer during cooking. So what happens when we switch on our stove or our cooker. So what happens when the heat from the stove or the cooker, how it touches our pots, and from the pots to our food. So that's what thermodynamics explains what happened within those processes, the processes of cooking, the processes of pasteurization. And pasteurization is like cooking in low heat. Sterilization is also the process of cooking in high heat and freezing. It also controls evaporation rates in drying, concentration, and hydration process. So that is why food science is related to um thermodynamics. So the next thing, we move to the common terms in thermodynamics. Thermodynamic system and its type. The first term that we need to know is our system. So our system is the region under study, which may be a specified volume in space, a quantity of matter. So I mentioned earlier that our involved matter is our system. So our system is a region under study. If you check that diagram that is within, there's a large space, then the small aspect of it, a smaller compartment, a smaller aspect that we are focusing on, that is our study, it is our region of study. That is what we call our system. Now, our surroundings. Surrounding describes the rest of the universe. Surroundings is the rest of the space that we are not concerned about. Surroundings is the rest of the universe that we are not concerned about. Then our boundary. Our boundary, it is the part of the universe that separates the surrounding from the system. More like a thin line that separates the system from the surrounding. And please note, the system can be like a volume in space or a quantity of matter. So that's basically all we need to know about system, surrounding, and boundary. If you understand what these terms are, you won't be confused when we start solving calculations concerning it. So now that we've established the definition of system, let's move to thermodynamic system. So we have three basic type of thermodynamic system. The first one is our open system, and it says if the thermodynamic system can exchange both mass and energy with its surrounding. So we can call that system an open system if it can exchange both mass and energy with its surrounding. It can exchange mass and it can also exchange energy with its surrounding. Then our closed system, if the thermodynamic system can exchange only energy with its surrounding. So in this case, unlike open system, our closed system can only exchange energy with its surrounding. It cannot exchange mass with its surrounding. Then the third one is our isolated system. So if the thermodynamic system can neither exchange matter nor energy with its surrounding. So our isolated system, unlike closed system and open system, it cannot exchange anything with its surrounding. It cannot exchange both matter, it cannot exchange both mass rather, it cannot exchange both mass, and it cannot exchange energy too with its surrounding. So basically it's just like 2 1 0. Like the first one can exchange two things, and that's mass and energy. Second one can exchange just one thing, and that one thing is energy. And the third one cannot exchange anything, it cannot exchange both mass and energy. So the next thing is we move to the properties of system. Thermodynamics. The property of a system is the characteristics that defines that state. So basically, when we are talking about the property of a system, that means that system, the characteristics that define the system. So it can either be an intensive property or an extensive property. So intensive property now, they are independent of the system size or amount of a substance, which implies that they do not depend on the size or amount of a system. So as you change the amount of substance, the property does not change. Examples include temperature, pressure, density, specific heat capacity, thermal conductivity. So now, let me give an example of an intensive property. So, for example, when you have like a water in a cup, yes, if you have water in a cup and the temperature of that water is less than 100 degrees C. So, when you pour from the cup into another cup, the level of water has reduced in that first cup, level of water has reduced. But does it change the temperature that is inside that cup? No, it does not change the temperature of the cup. So that's why they said intensive property are properties that they do not depend on the size or amount of substance. The size of the water reduced in that cup, but the temperature still remains the same. Temperature does not change, same as pressure. When the size of probably a water in a cup reduces, it doesn't mean the pressure that is in that water decreases. Do you understand? So they do not depend on the size or amount of a substance. An example is like temperature. So anytime you want to know if this property is an intensive or extensive property, the first thing that should come to your mind is, when that thing reduces, does it change the characteristics? So if it does not change it, then that means it is an intensive property. So, and they said examples are temperature, like the example I used for temperature, then pressure, density, specific heat capacity, and thermal conductivity. There are still a lot more, but these are just the examples that are common. So they're usually denoted in lowercase for temperature and pressure exemptions. So when you want to denote, or when you want to write intensive property, like when you are not writing temperature, when you just want to write the units, they're always written in lower cases, but there are exemptions of temperature and pressure. So the next one is our extensive property. They are dependent on the system size or amount of substance. So these ones depends on the size of the system. It depends on the amount of substance, like the example that I gave initially of a cup of water that is, let's say, a cup of water that is filled to the brim. And so if you pour from that water into another cup, the what's it called, the size of the water has reduced, which is the mass of water. So the mass as you produce, the mass of the water has reduced. Sure, you get. So those are examples of extensive property. They depend on the size and the amount of substance of a system. So the property varies with amounts, like have explained. Examples include mass. So let's say the mass of water in a cup is 100 gram. So when you pour from it, it has reduced to like probably 75 gram or 50 grams. So it is dependent on the amount of the it is dependent on the amount, then volume too. So let's say the volume of water too, the volume of the water is, let's say, 1000 liter, and you remove from it, so it can reduce to what's it called, can reduce to like probably 750, or yes. So, and examples, the further examples are energy, entropy, and enthalpy. They're usually denoted in uppercase with mass as an exemption. These ones are denoted in uppercase, but there's an exemption of mass. So now, in summary, intensive property do not depend on the amount or the size of the substance, but extensive property depends on it. Yes. So for the last thing we're talking about on this section is the laws of thermodynamics. Yes, laws of thermodynamics. Laws of thermodynamics. So we have the zeroth law, the first law, which is law of conservation of energy, the second law, and the third law, which is absolute zero. So if the zeroth law states that if two systems are in thermal equilibrium with a third party, they're also in equilibrium with each other. So that just translates us know that if you have two systems that are in equilibrium, and there's also a third system that is in equilibrium, they are all in equilibrium with each other. So that's what zeroth law is talking about. Now the first law, which is the conservation of energy, we are quite familiar with that. Energy can neither be created nor destroyed, but can be converted from one form to another. It implies that you cannot create, like from one system to another, you cannot create or destroy energy, but you can convert them from one form to another. And the second law, it says that total entropy, that is the disorder or randomness of a closed system, always increases over time. This second law is just basically telling us that temperature moves from a degree of higher temperature to lower temperature. All of these are just English. So it's just like that's what the second law is basically telling us about. Then the third law, which is absolute zero, says that as temperature approaches absolute zero, entropy approaches a minimum value. So as it's more like saying as temperature decreases, entropy also decreases, because as temperature approaches zero, entropy approaches a minimum value. So guys, that's it for today. Our next section would be calculations on first law of thermodynamics. So till then, guys, see you later. I love you. Please, if you have not subscribed to this YouTube channel, kindly hit the subscribe button. Make sure you like, comment. If there's any question that you have, please drop it in the comment section. I'll reply you. And guys, until next time, see you guys later. Bye.